Okay, so my project is on predicting the abundance pattern of heavy nuclei in a binary neutron star merger using deep learning models. So now let's understand what does that all mean. So basically, a neutron star merger is when two neutron stars collide, and that is a uh, very neutron-rich material place, where our process nucleosynthesis takes place. And what I want to do is predict how what the elemental abundances are going to be uh, in this place, and what are the elements we are forming, and does that explain? Does that see like what we see in life? Traditional nucleosynthesis simulations are very computationally intensive and depend on large nuclear reaction networks. That's why I want to make a data-driven model that learns the relationship between merger parameters like temperature, entropy, electron fraction, and gives us the final abundance, elemental abundances. So that's what I'm going to do. That's the project. Now let's understand what all does neutron star and neutron star merger and all what are that parameters and what are this means. So neutron stars are collapsed cores of massive stars left behind after supernova explosions. A star dies, the material gets a lot of the material gets ejected, and or the what is remaining is the collapsed core, which is now just made of neutrons in essentiality. And when there are two such neutron stars very close by, they orbit each other and they gradually lose energy through gravitational wave emission. Eventually, they spiral inwards and collide, releasing extreme densities, temperatures, and neutron flux. These collisions are called kilonova, and these places are very rich environment of neutrons and are therefore ideal environment for rapid neutron capture and produce heavy elements like gold, platinum, and uranium. The urgent ejecta contain both dynamical ejecta and disk winds, both contributing to the final abundance pattern. Making accurate models of the is essential for connecting theory of with observation of the kilonova spectrum. So, what are the key parameters that we've taken in? The key physical parameters driving the art processes are the following: density, the density which is extremely high, 10 to the power 12 to 10 power 14 grams per centimeter cube, and this determines the neutron availability. Next is the temperature, which can exceed 10 to the power 9 Kelvin, influencing reaction rates and nuclear equilibrium, just like which direction the reaction is going in. Electron fraction sets the neutron to proton ratio critical for heavy element formation. Much more is the neutron, the better, the more heavier the elements will form, like by our processes. Next is entropy, which governs the balance between nucleons and the seed nuclei. Next, again, is expansion time scales and controls how long our process can proceed before it freezes out. Basically, till how long the neutron-rich environment is still there, so that we can like make the heavy nucleus before it stops. Like we stop making more and more heavier nuclei. Next is the neutrino luminosity, which affects the electron fraction and neutron richness of the ejecta via neutrino capture. This tells us like how much effectiveness of the material was in making the material, like how effective the ejecta, how effective like the properties were in actually making heavy elements. Next is ejecta velocity, determines how rapidly the material is expanding, impacting the freeze out and final abundances. Uh, you know. Next, the last one, which we take in account, is ejecta mass, which controls the yield of our process elements and observable kilonova brightness. So basically, you need to know how much mass is getting out to know how much like of each mass you've made. Can't just be the percentages. The interplay play among these parameters define the astrophysical conditions that drive the process nucleosynthesis, and accurate modeling of these factors is crucial for reproducing the observed abundance distribution and understanding heavy element formation in the universe. Now, coming to the methodology of our project and what we have tried to do in our code and all. So, what we've done is first we have done data processing, in which we have normalized all the input parameters, and then split the data set into 80% training and 20% testing. We secondly made a we made a model architecture of multi-layer perceptron designed using TensorFlow and Keras. The input layer correspond to the physical parameters. We have multiple hidden layers with nonlinear activations and output layers that predict the final abundance distributions. In step 3, we did a model optimization. This model was optimized using dropout and early stopping and Adam and all and mean square error and all loss functions to prevent overfitting and regularization and all and everything. So, and then we did a model evaluation with R-square metrics and MAE metrics and compared the predicted abundance curve with the true abundance curves. So like we'll show you those curves to see how well the model did. Now the multi-layer perceptron design was like the following. We had input layers with the 8 features with like the parameters I told you about. We had 2 dense hidden layers with each with 64 neurons. I tried with lesser neurons and more neurons, and I found that the best results were around 64 neurons. Were around 64 neurons. We did batch normalization after each layer for faster convergence and stability. We had a dropout of 0.2 to reduce overfitting and improve generalization. L2 regulation applied to weights for smoother learning and all. We had an output layer of 201 neurons. So basically we wanted like basically 201 parameters for 201 different mass numbers. That's what like we were hoping for. So that was that. And then you can see, and this architecture captures complex nonlinear relationships between physical conditions in neutron star mergers and the resulting R process abundance balance. The combination of normalization, dropout, and regularization ensures stable and accurate training. So now let's, I guess, first look into our code before we see what the results were like. So let me get the code on the screen first. Okay, give me 2 seconds for that. Okay, so okay, this is our code we made on CS code, and I made my own what do you say, and my own environment in WSL and using that environment I've run the code. So if you want to run the code, please properly install the environment first, because that has like uh, very specific versions of them, because it wasn't running on other versions. So I have run the code before, and I'll just tell you what all the blocks means. This is just an import block and wanted to see like all of the versions were loaded properly. For some reason the matplotlib version is not being stated, but like it's there. I don't exactly remember which one, but it is there. Then we loaded the data. We loaded the data with correct form, like whatever the data form could be. If someone is using different data form, they can use this again. So that's why I wanted to just support all of them. And then we loaded the data. Then we did a pre-processing. We did scaling and all of that, and conversion and all, which I talked about, and then distributed into tests and all. Then we defined the model. Our model is like this. This is our model, and we made a model into. We made our model. We compiled the model, and then we started with training. So we trained our data, and it ran for a long time of, I guess, 9 minutes. And considering how long the processes are for each of them, like it could take days, this is way less amount of time of training and all than it will take. And after training, it just runs very quickly on the data, so it doesn't really matter like how long it takes training also. I mean, it does matter, but not as much if you're getting the output reliably and fastly. So it ran for 130 epochs, and then after that it stopped training because or else it would be overfitting. This was our training versus validation loss curve, and then we evaluated the evaluated on test data, and then it ran in approximately 4 milliseconds and all. So that's really good and all. So after doing that, this is our results and all. So this is what like kind of curve we got. So this is for different mass number index. I don't exactly remember for what mass number it is, but this is not like this zero is not for zero exactly, but from some high range. Anyways, so this is how the blue one is the true and the orange one is the predicted one, and it models it somewhat accurately, and I think that's good enough accuracy for the start of this project. And this was visualization and all. This was the predictive versus true abundance scatter diagram and all. And I was trying to show you the values which we got, and I'll tell you what those values means and all. And we got this as a residual distribution and all. So I'll get into what the results were properly now, and this was just our code. I'll try to show you some more. Okay, those are saved ones which I'll show you in the slides again. So now let's get back to the slides. So this was the curve which you saw. So what does this curve actually mean? This means that the training and validation loss curves converges smoothly, indicating stable learning and minimal overfitting. Early epochs show rapid loss of reduction before plateauing, suggesting efficient optimization. Now, 1 second, right? So, okay. Now we'll get to what the other metrics mean. So we got which this was other metrics were down. So we got an 8 point like MSA and MA very small values these are. So like the absolute error is very small. We got an R2 square of 0.81, which could be improved in further this, but it for the start is very good. And we got a correlation coefficient of 0.904. These metrics show strong correlation and accurate reconstruction of the true abundance pattern. So now we'll get into the more of these curves which we saw. So we can see that in this curves the modeling has been done very nicely, and even in the lighter to much more heavier, it's like very nice. In this it's a bit off, but it's still very good for how we have started right now only. And you can see that like in the predicted one there is like some amount of variance that there is, which on the top like that, and over here as well. And this is like best model in this. I feel like in heavier ones where it goes up over here at the almost at the same times, and it's very nicely predicting it. So this is like just the start of the prediction, and we need to improve our code and all. But it's very good for the start. Okay, so now we'll go to the next slide. So our curves show that the predictor curve closely follow the true data, and the MLP model effectively reproduces the major R process abundance peaks across the mass number range. The minor deviation which appear are likely due to limited training data or physical noise. And the results confirm that the deep learning model successfully learns the complex nonlinear relationship between astrophysical parameters and final R process abundances. The strong R2 and correlation scores demonstrate the MLP can serve as a fast surrogate model for nucleosynthesis simulation, drastically reducing the computation time while maintaining accuracy. Although we do need to get the model even better, which we are going to discuss in our future directions. So our future directions could be we can extend this to multi-merger or black hole neutron star systems for broader astrophysical coverage. We can include time-dependent evolution of ejector properties and nucleosynthesis rates. We can integrate physics-informed neural networks to embed nuclear physics constraints directly into training. We can incorporate data. We can incorporate larger and higher resolution data set, and then We can apply feature selection and dimensionality reduction to identify the most influential parameters to reduce the complexity even less, to reduce the complexity even more and get even faster results. Explore ensemble deep learnings like other models and combining the other models with each other for improved prediction and robustness. And we can also we can validate our predictions with spectroscopic observation of kilonova and metal poor stars. We can compare the predicted abundance peaks with empirical solar system R-process residuals. So those were the future predictions. And now I just want to discuss what the outcome of this project was. We demonstrated the potential of machine learning as a surrogate for computationally extensive nuclear synthesis model. This model enables rapid parameter scans and uncertainty quantification across diverse astrophysical environments. Provides a bridge between astrophysical modeling and data-driven discovery in nuclear astrophysics. So this project establishes a foundation for combining deep learning and astrophysics to decode complex R process behavior. With expanded data and physics awareness models, such frameworks can significantly accelerate the exploration of element formation in extreme cosmic events. So that was my project, and I just want to say thank you for this opportunity, and that would be it. If you have any questions, you can reach out to me. So thank you.